We are going to start one of the most popular topics in machine learning, namely the learning of decision trees. Now, decision trees have been there for many years. Decision trees offer a nice way of representing the necessary criteria behind making decisions. So it has been widely used in the past in management, for example. When you want to explain certain decisions that the management is taking, then they like to show it as a decision tree so that it becomes easy for the people who are in the audience to understand what is the rationale behind taking a decision. More recently, with statistical machine learning, decision trees are learned in the sense that I have data and I need to take certain decisions based on the data, and the decision tree which is learned tells me that what influences the decision, and accordingly that provides explainable information to the user for making decisions and automating the process of decision making. So we start by looking at what we mean by a decision tree. So it takes as input an object or situation described by a set of properties and outputs a yes/no decision. So the most basic form of decision tree learning is where for a specific decision variable you try to determine whether, based on the data and the given circumstances, should your answer be yes or no for that decision variable. We start with a classical textbook example to explain how decision trees are learned. So this is a example where the decision variable or the variable describing the decision that we want to take is whether to wait for a table at a restaurant. So you have gone to a restaurant with your friends, and depending on several criteria, you will either decide to wait for a table at the restaurant if you do not get a table immediately, or you will decide not to wait and go for other arrangements. So if we look at the different criteria which may affect the decision to wait or not to wait for a table at a restaurant, here are a list of 10 such attributes which could possibly influence the decision. We do not know a priori which of these are actually relevant, but we note down that, well, these could be possible reasons for deciding to wait or not to wait. So the attribute 1 is that whether there is a suitable alternative restaurant, that is, in case I do not wish to wait for the table at this restaurant, are there other restaurants nearby where I may go and try to get a seat there. The second criteria is that whether the restaurant has a lounge. If it has a very comfortable lounge for waiting customers, then I may decide to wait here. Otherwise it may be pretty hot outside, so it might be a better option to just wait at the lounge. The third criteria is whether it's a Friday or Saturday. As you know, on Fridays and Saturdays the rush is more. So if you see there is a waiting queue in Friday or Saturday, then it is unlikely that you will get a table quite soon. So based on that, you may decide to go to another restaurant, whereas on a Monday or a Tuesday you may decide to stay on the same restaurant, hoping that, well, the rush is not so big. The fourth criteria is of course very important, that is whether you are hungry or not. If you are very hungry, then you may prefer not to wait, and you may actually go and have your lunch in some fast food joint where the waiting time is less. You would also like to see patterns, that is how many people are in the restaurant. Now if you find that the restaurant is empty and still you are not being given a table, then you will be somewhat put off and you might walk away. If you find that there are some people, then you may decide to wait. If there are If the restaurant is full, then you know that, well, the waiting time could be significantly higher, and then accordingly you may decide to wait or go away. Price, of course, is another very important thing. Depending on the price rating, which is single star means it's a budget restaurant, double star is average, and triple star is it's a high-end restaurant. So depending again on the star rating of the restaurant, that is the price value, you may or may not decide to wait. The seventh criteria is whether it is raining outside. If it is raining, then you may prefer to stay here and not really make a dash for another restaurant in the rain. Then you may look at reservation. If you had a reservation in this restaurant, then you may prefer to wait, because you know you have priority, so the restaurant is committed to provide you a seat. Whereas if you go to another restaurant, they may or may not commit to give you a seat. Then type, that is whether it's an Indian restaurant, Chinese, Thai, fast food, etc. That may also influence a decision. And finally, the wait estimate provided by the restaurant. So they may say that, well, we anticipate that you will have to wait between 0 to 10 minutes or 10 to 30 minutes or 30 to 60 minutes, and some restaurants may say, well, sir, I'm sorry, we cannot accommodate you before 60 minutes. So based on these criteria, we may be taking the decision to wait or not wait. Now, in the automated way of learning decision trees, the input is data. So someone has collected this data from various restaurants, and from those restaurants they have found out that for different situations, different people take a yes decision or a no decision. So if you look at this table, you see that for those attributes there are many different combinations, and corresponding to that, the decisions are there. Now it may so also happen that for the same combination you get sometimes yes and sometimes no. We are going to come to that later on. But as you can see that there are actually pretty much a lot of varieties, and consequently we also need a significant amount of data to make any meaningful estimate of what actually influences the decision. So for example, in this, if we look at the first row, then what it says is that yes, if there is an alternate restaurant available, if the present restaurant has a lounge, if it is a Friday or Saturday, you are not hungry, the restaurant is full as of now, it's an average priced restaurant, it's not raining outside, you have a reservation, the restaurant type is French, so it's a French cuisine, and the restaurant says that your waiting time is anywhere between 10 to 30 minutes. Then this person for whom the data is given here decided to wait, so the decision was yes. And similarly, each of these rows corresponds to a different data item, corresponding to some customer waiting in some restaurant with some values of these attributes. Now, given this data, we would like to come up with a decision tree which looks something like this. So you are first examining patrons, and you are saying that, well, if there are no patrons, that is the restaurant is empty and they don't give you a seat immediately, you will not wait. So there the answer is a definite no. If you find that there are some patrons, that is some people are in the restaurant, then you will wait. On the other hand, if it is full, then you will seek what is the wait estimate. If the wait estimate is less than 10 minutes, you will wait, so the decision is yes. If the wait estimate is more than 60 minutes, then the decision is no. On the other hand, if the wait estimate is between 10 to 30 minutes, then depending on whether you are hungry or not, then you will take a decision. So for example, if you are not hungry, then you will wait, so the decision on that branch is yes. On the other hand, if you are hungry, then you will seek, is there an alternative? If there is no alternative, then you will wait. So the decision there also is yes. If there is an alternative, you will seek, is it raining? If it is raining, then you will wait. So there also the decision is yes. But if it is not raining and you are hungry and there is an alternate, then you will not wait. So to read the decision tree, you start from the variable at the root and examine each of the variables in the scenario for which you seek the decision, and based on the evaluation whether you reach a yes node or no node determines whether you are going to wait at that restaurant or not wait at the restaurant. Now decision tree learning is about learning how we can construct this decision tree from the data. So we are given the data, the table that you saw in the previous slide, and the output of the decision tree learning algorithm is the decision tree that you see here. Of course, the data that I showed in the previous slide is only a subset of the full data. In the real data, we will have many such rows based on which it will take this statistical learning to come up with this decision tree. So the decision variable here is, does the customer wait for a table, and the attributes are chosen such that they influence the decision based on the evidence or the data provided. So let's look at the basic idea of constructing a decision tree. So we need to choose attributes that will form the nodes of the decision tree. So we start from the root. So at the root we will try to select a variable which acts as a good discriminator between the yes cases and the no cases. That is, the cases where you decide to wait or the cases where you decide not to wait. Now a decision variable, an attribute, is not a good choice if you find that the value of that variable does not really take you any closer to deciding whether your decision to wait for a table will be yes or no. We are going to come to that in a moment, that how we go about choosing that attribute. But suppose we choose the attribute patrons as the root. Now in your table, the table that we saw, for patrons there are some entries, some rows where the value of patrons is none, that is, there is nobody in the restaurant. For some of the rows the value of patrons is some, and for some of the rows the value of patrons is full. So when you choose the patrons as the root of the decision tree, the set of rows will then be distributed among the branches. So in the none branch in the decision tree, I will put all those rows for which patrons was none. For the branch which goes from patrons with some, I will put all those rows for which patrons was some, and for the remaining ones, that is the rows where patrons was full, will go into the right branch of the decision tree. So now what you see, okay, let me start a bit of annotation. Just give me a moment. So what I am saying here is that in my table I had these rows, and in some of these rows the value of patrons, that is, in some of them I had none, maybe for these patrons was none. Then for some of the rows, well, there were other attributes of course. for some of the rows it was sum, and for some of them it was full. So these are the rows that you saw in the table that I showed you. Now all these rows will now be used here in this node. All these rows will go into this branch, and the ones corresponding to full, they will go into this branch. So based on the attribute value, I have these three branches, and my data items here, they get split into three parts. The rows which had none, they go here. The rows which had some, they go here, and the rows which have full, they go here. Now for these, as we shall see in the decision in the data, all of the entries here, the decision was no. And for the sum cases, for the ones where patterns is sum, everywhere we have yes. So because I have the decision fully taken here as no, and here the unanimous decision is yes, so these nodes do not need to be expanded any further. Whereas for the full one, sometimes we have yes and sometimes we have no. So we know that when patterns is full, it's not a unanimous decision to wait or not to wait. So we need to look at other variables. So then what we do is we recursively apply the same algorithm with this part of the data and with this as the root. So then we choose from these another attribute which will be the root of this subtree, and then weight estimate is chosen, and then again the same process is recursively followed. So that's the basic idea of constructing the decision tree. We shall see in more details as we go along that how we choose the attributes and how do we split, and then how do we recursively apply the algorithm again. So as I mentioned that we first find an attribute which helps in separating the yes answers from the no answers to the extent possible, and we make it the root. We then split the data based on the values of the chosen feature, and for each subset thus created, if the subset contains all yes or all no, like for this case we had all no, for this case we had all yes, then we create a leaf with that decision like we did here for no and yes. But otherwise the subset contains some yes and some no, and we recursively use the first two steps. That is what we do here for the weight estimate. Okay, so that's the idea of creating a decision tree. We may sometimes terminate the recursion earlier. So we may at some time also take a decision, let's say somewhere here, let's say we take a decision even though at this point also I had some yes and some no. So it could be the case that the patterns is full, weight estimate is between 10 to 30, I am hungry, there are alternative restaurants, and it is not raining, and in overwhelming majority of cases I have no, but in some cases I have a yes. So then I may override the yeses and simply terminate the algorithm here by saying that when I have this combination, then the decision is no. And we are going to come to that, because if we still keep on expanding beyond a level, then we may end up with overfitting. And you may recall that in the first lecture on machine learning, I did point out that overfitting is a problem when we choose when to, of what capacity we wish to choose for a particular machine learning model. So the key question here is which attribute is a good discriminator between the yes and no decisions. So let's start by looking at patterns. How good is patterns as a discriminator? How good is patterns as the first choice of variable? So the good thing about patterns is that, as you can see, in the cases where I have sum, that is where patterns value is sum, in all of these cases my decision is yes. And in the cases where patterns is none, in all of those cases my decision is no. So that gives me a nice branching, because I know the branch corresponding to sum will end in a leaf node, the branch corresponding to none will end in a leaf node, but for the branch corresponding to full I cannot take a decision yet, because there are some yeses like here and there are some no's as well, as you can see here. So I cannot take a decision there. So if you look at this in a different kind of notation, then you can see that initially in my data set I had 8 yeses, so my greens are yeses and the reds are no. So if you look at the data set at the beginning, there are 6 yeses, that is 1, 2, 3, 4, 5, 6 yeses, and there are 6 no's. Okay. Now when I choose patterns as the root variable, then here for none I get only no's, for some I get only yeses. So that means that I can immediately mark this as a yes leaf node, I can mark this as a no leaf node, and here I still have indecision, in the sense that there are 2 yeses and 4 no's, right? So we need to look at other variables. So patterns from this point of view seems to be a good choice. And now let's see what is not a good choice. So for example, if you look at the type of the restaurant, is that a criteria which makes me decide to wait or not? Well, that seems to not be the case, because if, for example, if I look at French cuisine, then in the data I have one person who waited and one person who did not. If I look at Italian, then there is one person who waited, one did not. For Thai, 2 people waited and 2 people did not wait. For burger, 2 people waited and 2 people did not wait. So as a discriminator, type is not a good variable, because it does not take me any closer to the decision of whether I will wait or not. Whereas pattern was nice, because at least on 2 out of the 3 branches I had a definite decision. Now, to capture the notion of influence that an attribute has, we can think of something called an entropy. Now, if you remember your chemistry and physics lessons, particularly when you studied thermodynamics, for example, we have high entropy when I have more amount of chaos in the data set. So for example, here it is very ordered, everybody is no. Here it is very ordered, everybody says yes. Here it is not so ordered, because I have some yeses and some no. So if I arbitrarily choose a sample, the decision can be, say, yes with 2 out of 6 probability, and the decision can be no with a 4 out of 6 probability. But the probability is not, good enough to tell me that yes, well, 99.99% of the time, or maybe 100% of the time, the decision is yes or the decision is no. So that's where we bring in what is called an entropy measure to decide what is the good choice of the variable. Here there is more chaos, because if you ask that, well, if you are going for a Thai restaurant, then is that a discriminator for deciding whether you wait or not wait? The answer is no, because with 0.5 probability I will wait in a Thai restaurant, and with 0.5 probability I will go away. So that does not help. The decision tree learning algorithm is actually quite simple. As I explained, that what you do is that in each iteration you check the following. You see if all the examples, all the data points have the same classification. The classification here is the decision. If all of them are saying yes, then you simply return the classification. This is what is a leaf node. So a leaf node is where you have all data of the same classification. All are yes or all are no. Or if you find that you have run out of attributes, which is the case when you have several data, and then now you see that in all these data items, say in all of them, each of the attributes have the same value. They have the same value, but in some places you have yes and some places you have no. So then what will you do? So then you take the majority. So you take the majority, which is indicated by this mode. So you take the majority and you return that. So if there are 3 yeses and 1 no, then I go by yes. Okay, that's when I run out of attributes. That is, I have already included all the attributes. As we shall see later, that sometimes even though you have not run out of attributes, you may choose to limit the number of attributes that you are going to include in your decision tree, and therefore again take a statistical decision if you reach a node where you still have yeses and nos. Otherwise, in general, what we do is we choose the best attribute, which is what we are going to see next. How do we do that? And then what we do is we split up that node in terms of the branches corresponding to each possible valuation. So for each value that we have for the chosen attribute, we add a branch to the tree with that particular label, that is particular value. Like we had for patrons, we had some, we had full, we had none. So those are the 3 branches. And what we do is that along the branch, along each subtree, we look only at those values, those rows which have that value. So for example, for the ith branch, I look at only those examples or those rows where the value of the attribute is vi, right? And then the tree gets split up accordingly, and then recursively we apply the same algorithm. As you can see here, I recursively apply the same algorithm, and we keep on doing that until we reach the leaf nodes. So let's now come to the most important part of it, that how do we choose the attribute based on which we will split the decision tree. So again, coming back to the example, we saw that patrons is better than type, because patrons at least take some decisions on some of the branches, but for the type we cannot decide on any of the branches. It's still very equally probable that I will wait or not wait on each of the branches. So we will use an entropy metric, but to understand entropy, let's first take a small primer on what entropy means. So entropy and knowledge are very closely related. So we will try to understand entropy by looking at a simple example to understand how statistically we can derive entropy. So here you can see there are 3 buckets. Bucket 1 has all red balls, bucket 2 has 1 blue ball and the rest are red, and bucket 3 has 2 reds and 2 blues. Now if you look at the probability that a ball selected from bucket 1 is red, then that probability is 1. So there is no ambiguity in terms of the color of the ball that I can draw from bucket 1. From bucket 2, if I draw a ball, then with a probability of 0.25 it may be blue, but with a probability of 0.75 it is red. And in bucket 3, a blue and a red ball are equally probable, and they will come with a probability of 0.5. So how much information do we have on the color of a ball drawn at random? In the first bucket, we are sure that the ball will be red. In the second, we know with 75% probability that the ball will be red. And in the third bucket, we know with 50% certainty that the ball will be red. So bucket 1 gives us the most amount of knowledge, and therefore it has the least entropy. And entropy is the opposite of knowledge. So knowledge is order, that is, you know the relationship between various variables, so it reduces the degrees of freedom. And entropy is about chaos. So the lesser that you know, the higher is the entropy, because whatever you try to deduce about the system, you will end up with very low probability of being certain that it will take certain value or certain decision. So bucket 1 has the least amount of entropy here, and bucket 3 has the highest entropy. Now to come to a relationship between entropy and probability, we ask how many distinct arrangements of the balls are possible. So the first bucket, we have only one arrangement. For the second bucket, we have 4 arrangements, because the blue ball may come up at the end, or it may be the third one, it may be the second one, or the first one. For bucket 3, there are actually 6 different arrangements, as you can see here. The probability of finding a specific arrangement in 4 draws of balls is less for the third bucket, because the number of possible arrangements is larger. So we can think of a game. Where we are given a particular arrangement, okay, and we want to see. So suppose I am given an arrangement. Let us say I am given the arrangement R, B, B, R for the third bucket. So suppose for this bucket we are given an arrangement. Now I ask you that if I draw the 4 balls one after the other randomly without seeing them, then what's the probability that I will end up with exactly this choice? That is, I get the first ball is red, the second is blue, the third is blue, and the fourth is red. So from here you can see that the probability that I will pick up exactly in this order is 1 out of the 6 different possibilities, right? Whereas if you look at the second bucket and you take any of the combinations that are possible there, say RRBR, then the probability that I will end up with this sequence of drawing the balls is 1 out of 4, because there are 4 possibilities and this is one of them. So the higher the entropy, the lesser is the probability that I will pick up exactly one combination, or rather one sequence. So we can understand entropy by using this game. So the game says that we have these 3 buckets. We choose one of the 3 buckets. We are shown the balls in the bucket in some order. Then the balls go back in the bucket. Then we pick one ball out of the bucket at a time, record the color, and return the ball back to the bucket. If the colors recorded make the same sequence than the sequence of balls that we were shown at the beginning, then we win. If not, we lose. So if you look at this, suppose look at the first pattern, so all reds, then in the first bucket I will get the red with a probability of 1. So the probability of the first ball being red is 1, the probability of the second ball being red is 1, third one is 1, and fourth one is 1. So the total probability is 1. So the probability that I will get exactly this combination, or that is I will win in this game, is 1. Now think of this pattern. So this is from the second bucket. Now from the second bucket, when I was shown the balls, they appeared as red, 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 and then blue. Now what's the probability that the first ball that I pick up is red? So that is 0.75. And remember that the balls are being put back after each draw. So when I ask that what is the probability that the second ball is red, that is also 0.75 because I replaced the ball. Similarly, the probability that the third ball is red is 0.75, but the probability that the fourth ball is blue is 0.25 because there is only 1 out of 4 balls which is blue. Now if I take the product of this, then the probability that I will get exactly this sequence is 0.105, and then you see that compared to this and this, now my probability of winning has become significantly lesser. Here I was winning with a probability of 1, here I am winning with a probability of 0.1. And then let us look at the third bucket where I have 2 reds and 2 blues. So now you can see the probability of picking a red or a blue is equal and 0.5. So the probability the first ball is red is 0.5, second ball is red is 0.5, third ball is blue is 0.5, fourth ball is blue is 0.5. So my overall probability of picking up exactly that sequence is 0.0625, which again is much lesser as compared to the second one. Here it was 0.105, now it is 0.0625. So the more the chaos that we have, the probability that I end up picking a particular combination becomes even less. Now when we go for defining the metric, we observe that if I take the product of many probability terms, then the metric becomes very small and we will have precision problems. So what we do is, instead of taking the probability of winning as you see here, we will convert the probability into a sum. So what we do is we take the log of it. So for example, for bucket 2, instead of using 0.75 into 0.75 into 0.75 into 0.25, we now take the log of that, and the log will therefore be minus of log 0.75, minus of log 0.75, minus of log 0.75, and then minus of log 0.25. That comes out to 3.25. We put a minus outside the log so that the terms become positive. Otherwise, as you know, for any probability term is between 0 and 1, so the logarithm will become negative. So we put a negative sign outside that to make the logarithm positive. So we get a positive value for this term. So for example, corresponding to this, instead of this, we now use the log of it and we get 3.245, which is a better number, having more precision than 0.105. And then finally we take the average in order to normalize, because we don't want the probability to be dependent on the number of balls here, rather it should depend on the entropy. So therefore I divide it by 4 here, because there are 4 terms, and then I get this 0.81125. So entropy is then defined as follows, that if I look at, say, m is the number of red balls and n is the number of blue balls, then the entropy corresponding to a pattern is given by this formula. So for bucket 3, let's see, there are 2 red balls and 2 blue balls, so minus m by m plus n will be minus 2 by 4, and then if you look at the red balls, then that is 2 divided by 2 plus 2, and then for the blue balls I have 2 divided by 2 plus 2 as well. So then I get an entropy of 1. Entropy of 1 is like the maximum chaos, because you cannot really determine whether there is no bias towards red or blue. Red and blue are equally probable, so you have the maximum chaos. Whereas if you look at bucket 1, then n stands for the number of red balls, so I have 4 divided by 4 plus 0. The number of blue balls is 0, whereas here the number of blue balls is 0, so this term becomes 0, and this term also becomes 0 because log of 1, that's what we are getting here, by 4 is log of 1. So therefore I get 0 plus 0, which is 0. So here the entropy is 0, which means that there is no entropy at all, and that is true because I can with 100% certainty decide that whatever pattern I pick up will be all reds. And entropy for bucket 2 by similar application of the formula will be 0.81125. So it is not as bad as the third bucket, but it is quite inferior to the first bucket, because I cannot now decide with the probability of 1 that I get exactly the sequence that was shown to me. So now coming back to the decision tree learning algorithm, this is what we do. We find out the entropy of the original data set. So how do we do that? We do it by using this formula, where as you can see that what I am doing is I am summing up these terms, the terms that you saw in the previous case. So for example, if I have in my initial data set, if I have p yeses and n nos, then my entropy is this, the one that you see here. This is my entropy, using the formula that we saw just now. So let me see, what was my initial entropy? What was my initial entropy when I had in my initial data set? I had 6 yeses, I had 6 yeses, and I had 6 nos in my initial data set before I chose the root of the decision tree. Now if I had 6 yeses and 6 nos, then this p by p plus n term, this will be simply 6 by 12, and then I take the log of them and I multiply it by again half year, and if we do that, we will end up with something very similar to what we had for bucket 3. That is, we will get minus of half log half, and then again minus of half log half, and then we saw that what you get out of that is an entropy of 1. So in this case, for my initial data set for the restaurant, my entropy was 1. Now let's see how a choice of attribute can reduce the entropy. So when I break up the set of samples, so for example, I had say patrons, and then you remember that for patrons, for some, what did we have? Just let me check. For none we had 2 no's. For some we had 4 yes, and for full we had I think 2 yes and 4 no's. does that all add up? Did I miss something? 2 yeses, 4 no's, yes. Right. So now here I can see immediately that here my entropy will become 1. Here my entropy will also become 1, and here it will become something else, let's say some theta. Now see, the number of samples that went down this way were 2, the number of samples which went down this way was 4, and the number of samples which went down this way was 6. So therefore we also need to weight these entropies with the corresponding numbers so that we get a proper value of the entropy of the system after we have chosen patterns as the root node. So therefore we define something called an information gain. An information gain is the same as reduction in entropy. That is, how much is the entropy reducing by virtue of choosing that as an attribute. So this is my original entropy, the one that we had. In our case it was 1, and we find out the remainder. The remainder is what we get by adding up these things. So as you can see, this term here, the term that you see here, this is the entropy of each of the branches. So for the first branch the entropy is 1, for the second branch the entropy is 1, and for the third branch the entropy is theta, whatever it comes by choosing p is equal to 2 and n is equal to 4. So then what I do is, for this one I will weight it with the corresponding weight value, which says pi plus ni is the number of samples which went down that branch. So pi plus ni here is 2, and what is the total number of branches, total number of samples that I had? P plus n, that was 12. So 2 by 12 into 1, that corresponds to the first term. Then here I had 4 samples which went down this way, so this one will be 4 by 12 into 1, and here I had 6 samples, so it will be 6 by 12 into theta, where theta is the entropy corresponding to 2 yeses and 4 no's. Okay, so that is how we compute the information gain, and then we choose the attribute with the largest information gain. So let's look at it here. So if you look at the information gain for patterns, which I worked out just now, you have 1, which is the entropy of the original data set. In the original data set I had equal number of yeses and nos, so my entropy there was 1. And then when I look at the 3 branches, so this corresponds to the left branch, where I have 2 samples out of 12, so the weighting factor is 2 by 12, and I then compute the information of I01, that is the entropy corresponding to 0 yeses and 1 no. Okay, and then this corresponds to the second branch, where 4 out of 12 samples are present, and here I have all the yeses and there are no no's. And then I have this for the third branch, where I have 6 out of the 12 samples, 6 out of 12 samples, and the entropy or the information gain, the entropy comes as 2 by 6, I 2 by 6 and 4 by 6, because there are 2 yeses and 4 no's. Okay. Now when you compute that, then I get 0.0541 as the value of the information gain. On the other hand, when I look at the information gain for type, then as you can see here again, the original entropy is still one, because that's what we started with, and I have that as 1. Then if I look at the first branch, there are 2 out of 12, but then 1 out of 2 says yes and 1 out of 2 says no. Then similarly for the second branch, which is Italian, for the branch corresponding to Thai, we have 4 out of 12, but then 2 out of 4 says yes and 2 out of 4 says no. And then this is for the fourth one for burger, where I have the same thing, and now when I compute this, it comes to 0. So the entropy, the information gain is 0. So here the information gain is 0.0541, here the information gain is 0. So patrons has the highest information, as it turns out for the data set that we saw, patrons has the highest information gain of all the attributes. So what are we going to do? We will try out on the initial data set corresponding to each of the attributes what is the information gain, and then we choose the one which has the highest information gain. Remember that this is a greedy choice. There is no guarantee whatsoever that if you choose the attribute which has the highest information gain as the root, you will definitely get the shortest decision tree. There is no such guarantee. However, as a greedy choice, it seems to make sense, because I want to start with an attribute which kind of resolves the chaos to some extent, brings some amount of order, and thereby increases the information gain. So I think that should be good enough for understanding how we create the decision tree. So let me recap once again. So at every iteration we look at all the attributes, and based on the data that we have, we find out the entropy of the data which has been given, and then we look at the entropy corresponding to the samples that we get in the different branches for the choice of an attribute, and based on that we compute the information gain for that attribute, and the one attribute which gives me the maximum information gain is chosen as the next attribute, and then the samples are distributed across the branches depending on the value of that attribute, and then recursively on each of those branches which still do not have all yeses or all nos, we apply the same algorithm to choose another attribute to again increase the information gain. Now this can continue until I have all yeses and all nos in all of the leaf nodes, but in some cases that may need to include all the attributes, or at least a vast majority of the attributes in the data set. Whereas it may so happen that some of the attributes are just incidental, and it's just by a stroke of probability that that they seem to influence the decision, but actually they don't. To see such a case, I created another example here. So this is exactly the same data set, except that I have added one more row here. Now if you compare this row, the row here with the row here, you will see that all the attributes that we have here, at least the attributes that we have displayed here, they are identical. And in this case the person decided to wait, and in this case the person decided to not wait. Now if we look at the trend, that when I have some patterns, as we saw that in the cases where I have some patterns, that is for these cases, I always wait. So if you see that the restaurant is not full and neither completely empty, you are willing to wait. But here we have an anomaly, because here this person was also in a situation where the restaurant had some patrons, but the person did not wait. Now suppose we look at the other attributes, the attributes which are not shown here but is there in the data set, because whoever created the data set also took into account many other attributes, but we did not use all of them for the decision tree. So suppose we found out that this person did not wait because the person had to pick up a child from the school. So that's why the person did not wait. Now picking up a child from a school is a one-off incident. That day that person had that responsibility, but in general, whether you wait for a table in a restaurant or not is not usually determined by whether you have to pick up a child from school. So the question is, do we bring in that attribute as another attribute in this table? That is, do we create another column here saying waiting child at school, waiting child? Should we put that? And then, because for many of these cases we won't even know, because for many of the people, that's not a factor, so it may not be applicable. So therefore, well, here it is yes, and in some cases it may be no, but in some cases we may not even know that whether the person has such a constraint or not. So now bringing in such variables constitutes what is called overfitting, because then you are trying to make the decision tree fit even the anomalies, but these are actually anomalies, they are like noise, so they will have to be filtered out. So that is why you may in some cases reach a leaf node and you say that, well, there may be other attributes, but you don't want to bring them in because they may not actually have a significant contribution to the decision, and therefore we may terminate at the same level, and we, instead of adding another node, we simply say that whenever patrons is sum, the decision is yes. And if there is an anomaly like we see here, where I have the decision as no, then we simply treat that as an anomaly and say that, well, that was a one-off case, but it does not really determine the decision in general. Okay. I will conclude with a few further readings. So decision trees are widely used in data sciences and management, as I mentioned at the beginning. The decision tree learning enables mining of relationships between variables towards influencing targeted decisions. So some recent directions in which similar types of structures and decision trees have been used are as follows. I've just noted down 3 of them, close to my heart, but there are many more actually. So the first one is Bayesian rule lists. So Bayesian rule lists are somewhat like decision trees, but instead of having a tree structure, they have a list like structure, where the list is like a nested if then else. So for example, the Bayesian rule list for Titanic, which tries to infer that what is the probability of the survival of a person in Titanic, can be expressed, you can learn this from the Titanic data set, that if a person is a male and an adult, then the probability that the person survived the sinking of the Titanic is around 21%. Okay, and we found that it actually varies between 19% to 23%, so on an average it's 21%. Otherwise, if the person is either not a male or not an adult, then if the person is a passenger of third class, then the survival probability is 44%. Else, if the person was traveling first class, then wow, just look at this. You have 96% probability. Now you know from the Titanic movie what this means. And the survival probability otherwise is 88%. Okay, so if you are male and adult, then the chances that you would survive is the least actually. Alright, and in the parenthesis, whatever that you see here, these things, they are the 95% credible interval for the survival probability. So with 95% certainty you can say that, well, they are distributed in that region. Decision trees for mining temporal relations is something which is gaining in significance, and in our research group also we are looking at this. So as you know, that time series constitutes a very important sequence of or type of data where you have data coming over time. So from industrial processes to stock market data to, for example, the waveforms produced by a circuit, or the voltage and current on a smart electrical grid over time. These are all examples of time series data, and a lot of medical data like Holter monitoring, ECG, etc. They all come under the broad umbrella of time series. And we often need to find out, particularly in case of unstructured time series data, we want to find out the temporal causes of events that we see. So for example, if you look at the sales of a company, and you have two curves here, one is for the sales and the red one is for advertising, and then I want to find out some pattern between the advertising and the sales, and I want to find out in what way does advertising influence the sales? Do they at all have any influence? And then what I want to do is to mine this data and come up with a relationship like this. Like we see that if there is low sales and high advertisement, then within 4 to 6 weeks, or rather after 4 to 6 weeks, we see high sales. Now this is a property which can be learned. It is not given, but I am given these time series data. I am given the red and the blue curve, and I analyze that data and come up with this. Now for coming up with relationships like this, again we can use decision trees, and decision trees are actually used in many cases where you have this kind of time series, including things like network management. Companies like the companies which maintain networks like Ericsson, they have to deal with managing the overall performance of the network over time, and they rely on the time series data from the past to take a lot of decisions, and then decision trees are used to come up with those decisions. So that's all for this particular topic. I hope you enjoyed it, and thank you for your attention. Have a good day.